The Cartesian coordinate system is a real number system. If the vertical axis, however, becomes the imaginary number line, like I have shown here, we can plot complex numbers z equals a plus bi as the ordered pair. So this is going to be the x coordinate is a and the y coordinate is b. This is called an Argand diagram. Just a way of plotting complex numbers. Now, we can actually use the same conversion equations to change these rectangular coordinates, which I've just described how you can plot them in rectangular coordinates, as polar coordinates on the complex polar plane. So for instance, let's consider this complex number here, 1 plus root 3i. If I type root 3 in the calculator, that's going to give me 1.73, so it's going to be something like 1 over and 1.73 up. It's going to be somewhere around here, I think, something like that. And so this is our complex number. I could write it like this, but we don't have to. We can just leave it as 1 plus root 3i. This tells us everything we need to know about it. And doing the actual conversion here, we're going to see that this, right, gives us 2. So we know the radius out is 2. This is 2 units out. And the angle, we get pi over 3. So this is going to be pi over 3. So this is the same thing as 2 pi over 3 on the complex polar plane. So as I said, we don't have to write the coordinates as 1 root 3. We can just leave it as x plus yi, or 1 plus root 3i, because that gives us everything we need to know about where the coordinates at in that standard complex form. If we can have a form like that for complex numbers in polar coordinates, however, that would be nice to have. To do that, well, as you can see, we already know that x equals r cosine theta and y equals r sine theta. So for the standard form of a complex number, we're going to just plug this into our x spot, plug this into our y spot. We get r cosine theta, r sine theta I, and then we can just, of course, distribute out the r to get this polar form here. And we know we already like that r is greater than 0. So we write r equal to the absolute value of z, because we always want positive r's, and that will always give us positive r's, as this. This is called the modulus, or the absolute value of z. Now the angle theta, this is called the argument. And the modulus and argument are always used in this context with complex numbers and plotting them on the polar plane. Now, if we're multiplying two complex numbers, we could, of course, just do, right, it's going to be a plus bi times c plus di. You distribute that whole thing, distribute that whole thing, you add it all up. Well, if we want to have this in polar coordinates, leaving it in polar coordinates from, instead of a plus bi, c plus di, multiplying it together in polar coordinates would be nice to know if there's any kind of simpler way of having it, rather than having to convert back to the rectangular, do the multiplication, then convert back to the polar. All right, so what I'm doing here is I'm multiplying two complex numbers, z1 and z2, and I'm going to multiply them together just to see what we get in the polar form. So z1 times z2, this is just z1 here, this is z2 here, and I'm going to move the r's in front so that they're just out of the way. I'm also going to distribute the cosine theta 1 into both terms. Same thing with the I sine theta 1. That's going to give me this long portion here. Now, there's a lot of things I can do to this. First off, I'm going to move this portion right after the first one. I'm also going to multiply the i's together to get I squared. Then I'm going to move these two portions here, and they both have I in it, so I can undistribute or factor out that I in front of it so that it's just the cosine signs inside that portion. Now, I squared equals -1, so that's just going to become a negative there. And this is still the same. I haven't done anything with that. Okay, this portion here, this is a sum of two angles inside of a cosine. And this portion is a sum of two angles inside of a sine. That's one of the trig identities that we've looked at. And so really what we get is that when two complex numbers multiply, their distance from the origin multiply, and the angles that they have add together. So it's really going to be you either lengthen the radius or shrink it if r is less than 1. You do that portion of it, and then you rotate it further by the angle that you are adding or multiplying on. So it's very interesting that the multiplication of a complex numbers goes to addition of the angles. Now, let's look at this on the complex plane. So here we have two complex numbers that are written in rectangular form. So let's write this in polar form to see what we get when we multiply it. So r equals the square root of x squared plus y squared. The square root of this is going to be 2 plus 2 is 4. That's just going to be 2. And the angle, we know this is going to be in this first quadrant, root 2 over 2. That's going to be something around here. It's going to be on a 45-degree angle, so we know this is going to end up being 45. If we do tangent inverse root 2 over root 2, that's going to be tangent inverse of 1. And that happens at pi over 4. Okay, so this is the same thing as the radius times cosine theta plus I sine theta. All right, first one's done. Let's look at the second one. R equals the square root of, let's see, it's going to be x squared plus y squared. All right, let's see, we're going to get 9 times 3 is 27 over 4 plus 9 over 4. Give me 36 over 4, which gives me the square root of 9, which is 3. Now, before I find theta, let's actually see where this angle is at. This angle is going to be negative 3 over 3. Let's plug that in a calculator to see what that is approximately. 2.5, 2.6 just about. It's going to be negative 2.6 along the x-axis, so it's going to be somewhere around here. And along the y, it's 3 over 2 is just the same as 1/2, or 1.5. It's going to be about right here. So this is the location of that point. So this is Z3 and this is Z4. Okay, now we know what the angle is supposed to be, or we know about where it's supposed to be. And actually, when we find this, we're going to have to do extra work for it. So we're going to have y over x. And the 3/2 and the 3/2 actually end up canceling here. Just multiply it by the reciprocal, and you're going to end up seeing it's going to be negative 1 over root 3. And this is true. Let's plug it in a calculator and see. It's going to give us a special angle. Gives us negative 30 degrees. So negative 30 degrees is this angle here, but we know that's not the correct angle. We want this angle. That's the same thing as negative 30 degrees from the 45, or from the 180 degree line. So that's going to give us This is actually going to be 180 minus 30, which is 150. Let's do it in radians, however, rather than degrees. So this is the same thing as 5 pi over 6. So Z4 is the same thing as 3 cosine 5 pi over 6 plus I sine 5 pi over 6 in the polar coordinates. Okay, now that we have both of our angles and polar coordinates, let's go ahead and multiply them. Again, to multiply them, we're going to multiply the radiuses together. So it's going to be 2 and 3. So we're going to have 2 times 3. And then we're going to add the angles together in the cosine. So the first one was pi over 4. Next one was 5 pi over 6. Plus I sine pi over 4. Plus 5 pi over 6. That's going to give us 6 cosine. It's going to give us 3 pi over 12 plus 10 pi over 12. Same process. So we get 6 cosine 13 pi over 12 plus I sine 13 pi over 12. So it's going to be a little bit past pi, because 12 pi over 12 is just pi. It's actually going to be, so whatever this angle is, that's pi over 4. We're going to add on to that here. So it's going to be something like this. And it's going to be 6 out. So I don't know how far that is. It's probably going to be somewhere around here, I would guess. Because 6 on the axis is going to be right here. That's probably going to be a little bit back, actually. I would guess something like this. And this is Z3 times Z4. But really all this angle is just the same thing here. So this is I'll do theta 3. This is theta 3. And we're just adding on to this angle here. That gives us our point. It's all the way out here. We can, of course, translate this back into rectangular coordinates. So we've looked at multiplication. Let's look at division next. We can do a very similar thing. So Z1 and Z2 are still the same things as we've defined above. This right here is Z1. And Z2 is this portion here. The radii are dividing each other. And we're going to just kind of separate this into 2 fractions. So the radii and this. We can do that because they're multiplying. And you can see I can break up this fraction over the addition. So we have cosine theta 1 from this portion and I sine theta 1 from this portion. So I have the same denominator. I can multiply by the conjugate because these are complex numbers on bottom. We have cosine plus I sine. And so that's what I have here. I just multiply by the conjugate, top and bottom. And on top, I can distribute this here on top as well. And when I factor everything out, or when I multiply everything out in bottom, multiply this out, and multiply this out, because they're conjugate pairs, the only thing that remains is the first thing squared, cosine theta 2 squared, and the second thing squared. Well, it's going to be plus I sine theta 2 minus I sine theta 2. I times I is -1. 2 negatives cancel, so the i's cancel with this negative, and we just get sine 2. If you're not convinced of that, actually multiply this bottom portion out. Multiply it out and see that it becomes cosine squared theta 2 plus sine squared theta 2. This, of course, is the exact same thing, so it's going to be the same thing on bottom. Cosine squared plus sine squared. This is the Pythagorean identity. It's just equal to 1. So this thing just equals 1. The same thing was true for this one. Which means we can just get rid of the fraction. There's no need for it. that's what I've done here. I've removed the fraction, and I've just written the top with the exact same thing. I squared happens from this portion multiplying this portion here, and the I squared cancels with the negative, so that becomes a plus. Okay, now I'm going to do some simplification. I'm going to move this portion here in front, and I'm going to move these portions to the back while also taking out the I, factoring it out. I've also flipped so the negative is second and the plus is first. That's just a minor thing. At this point, we can use, once again, the sum and difference identities. Okay, and so now you can see that division leads to a division of the radii and a subtraction of the angles. So let's look at this with Z3 and Z4 like we already looked at. So Z3 was 2 times cosine pi over 4 plus I sine pi over 4. Z4 is 3 cosine 5 pi over 6 plus I sine 5 pi over 6. So Z3 over Z4 is going to be the radii dividing each other, so 2/3. And then cosine going to be the top pi over 4 minus 5 pi over 6 plus I sine pi over 4 minus 5 pi over 6. Okay, it's the same thing as, of course, 3 pi over 12 minus 5 pi, or minus 10 pi over 12. It's going to give us negative 7 pi over 12. But this is not in the standard angle form. We need to have positive angles for that between 0 and 2 pi. So negative 7 pi over 12, this is the same thing as just taking 2 pi, which is the same thing as 24 pi over 12, and removing off 7 pi over 12. 24 pi over 12 minus 7 pi over 12. So we get 17 pi over 12. Okay, and that is the division of those two polar complex numbers. So let's graph this and see what we get. So back at our graph, we have Z3 and Z4. Now we're dividing it. So what we're going to do is we're going to shorten the length. It's actually going to end up being this fourth quadrant, because we're subtracting this angle, this Z4 angle off of Z3. It's about that long, so I would assume that this is going to be just about here, somewhere around there. And it's about 2/3 out, so I think it's just about here, the point wise. So that is what my estimate is for Z3 over Z4. Maybe it's not completely accurate, but if I wanted it accurate, I'd graph it on software. But you can see that the multiplication leads to addition of the angles and lengthening the radius or shortening it depending on what you're multiplying. And then division typically will shorten it, but it could also lengthen it depending on, again, how much you multiply. But you subtract the angles for the division. That's the important bit there.